All right, we're going to start chapter 6, and we're going to talk about trusses. A truss is a structure made of slender members pinned at the ends of the members. The loading also occurs at these pinned locations. Here, I've sketched a truss, so each of these members is pinned at the end to the other members. This structure then can be simply supported like a beam. Let's say this is a rocker here. And then if you're going to load the truss up, we could have loads at the locations of the pins in any way we want to have it. And because this is simply supported, we can treat the whole thing like a beam when it comes down to determining the reactions. So this would be like AY, AX here, and then we've got a BY over here. So all the members are pinned. There are no moments. All the loading and reactions occur at the pins. This is going to end up being a 2D analysis, so this is planar. And each member is a 2-force member, which means that each member is either going to be in some state of tension or it'll be in the opposite, some state of compression with the arrows reversed. But each member is axially loaded. Trusses can be used to build larger structures. For example, you could build a bridge out of a truss, and this is what a bridge schematic of what a bridge truss might look. Bridge using a truss might look like. Here we have a truss on either side of this bridge, and we have what we would call stringers down here, these shapes. Which take the load from the bridge deck and distribute it back to the trusses using the floor beams. The floor beams are these. They support the, well, those aren't actually floor beams, but if there were beams in this direction, they would be floor beams and support the deck. This deck actually is considered to have some support on its own. But so the deck lays on top of the stringers, and then the stringers bring the load back out to the trusses on the end. Here is a picture of an actual truss bridge. Notice that the bridge is simply supported on two sides on these abutments here. One here and the other here. And then so there's bearings here and bearings there. And those bearings will be similar to bearings up in our picture here with the blue lines, where at one point, you can't see it here, but at one point the bridge truss will be pinned, say here, And then over on this side, there'll be a rocker there where it's not pinned. The pin side will look like this on a bridge, and the rocker side will look something like this. You go out and look at a highway bridge, you will see that all highway bridges on your way home are only pinned, the beams are pinned in one location, and all the other locations, the bridge just sits on rocker plates. If we were to construct a simple truss, we can start with just a simple triangular geometry here and pin all these three members together. That's the start of a simple truss. Now all we need to do is add more members as we go, more pinned members, so on and so forth. Okay, let's look at how we would structurally analyze a truss. So say we have a truss like this, and this truss here has 3 pin members, and it is simply supported, meaning that we have a pin here at A, resulting in reactions AX and AY, and we have a roller here, statically determinate, simply supported. We're going to use the method of joints to analyze this pinned truss here. So first thing we're going to do is we're going to look at individual pins. So let's take a look at pin C. We're going to draw a complete free body diagram here every time we do this. So let's say this has a 500 Newton force on it. We've got 500 Newtons at pin C. We've got a force CA, and then we've got a force down here, CB. Now, the way we're going to do this is we're always going to draw our pins with the forces coming off, which will indicate that we have tension in our members. Because if we're coming off with tension, if we're drawing our arrows away from the pins, that means that in our member, to have equilibrium at the same location, the force has to be in the opposite direction and collinear. And if that's the case, for equilibrium in this member, I need a force down here equal and opposite to the force up here. So this would produce tension. So when we have the forces pointing away from the pin, that's tension. I went ahead and redrew my truss because I want this to be a 45-degree angle. And I want it to look right. Well, since we have all pins, there's no moments, so we can only use sum of forces. So sum of force in the y direction equals 0 equals actually, let's do the x direction first so we can be sure to get a value here. Sum of forces in the x direction equals 500 minus the force of CB times cosine of 60 degrees. And this is not actually a minus, it's a plus, because the way I've drawn this, both my forces are pointing in the positive x direction. So force of CB is then going to equal minus 500 over the cosine of 60 degrees equal minus 707.11 newtons. So that indicates that this is drawn wrong, but that's okay. We're going to leave it because I know that any minus I see is actually in compression. So this is equal to the force of CB. I'll mention that again later. So now, summing forces in the y direction, I get minus force CA, it's pointing down, minus force CB again. Again, we're just going to use cosine of 60. Okay, we're not using 60 degrees, we're using 45 degrees. Here, 45 and 45. Should have noticed that. So this equals the negative of that, which is going to end up being 500 newtons positive. So that's drawn in the correct direction. So I've found now the force in this member and the force in this member. Let's figure out the force in this member by using pin B. Here is my free body diagram at B. Notice I made the member forces always pointing outwards is the best procedure to use. I'll mention that again. And here's my reaction at BY the same way I drew it up here. So now I got sum of forces in the x direction. It equals minus the force of BA, this guy, minus the force of CB, the x component, so that's cosine of 45 degrees. So the force of BA equals minus, so I'm going to take the force of CB, which is minus 707, got to take it with the sign, times the cosine of 45. Force of BA equals positive, negative times negative is positive, positive 500 newtons. So that is drawn in the right direction. Finally, let's sum forces in the y direction just to get the reaction. We don't really need to do that. And that also equals 500 newtons, and it is pointing in the correct direction for my reaction. Now notice in all these calculations I use cosine of 45 degrees. I didn't concern myself with sine or cosine here because cosine and sine of 45 degrees equals the same value. So now that I've figured out the forces in all my members, any force that turns out to be negative means that my beam, because of the convention I use where I always draw my element forces outward, any force I get that's negative always turns out to be a compressive force. So let me draw all the forces at the pins in the correct direction now. So at pin A, I have this vertical force pointing down, indicating tension in the member. Here's my load, 500, and this force points up, meaning I'm going to end up with compression in my member. So member AB has a tension of 500 newtons. The arrow's drawn right. Force AB also has a force of 500 newtons in tension. As we can see, it's pulling the beam apart. At this pin, these are the correct directions. So this points in this direction. And we have a reaction here. And finally, we have a force of 707.11 in compression with the arrows squishing this element. And that's what our truss internal forces look like. And if you think about what's happening, this is trying to rotate clockwise. Makes sense.